Welcome to our discussion of algorithmic analysis. First, what is an algorithm? An algorithm is a clearly specified set of simple instructions that should be followed to solve a problem. Algorithms can be as simple as a recipe from a cookbook or as complex as code. In terms of code, we can analyze algorithms in two ways: the time that they consume in terms of real-time clock cycles or instructions, and the storage space that they consume. In terms of software development, we frequently want to compare the efficiency of two algorithms before we actually implement either, so that we can implement the best algorithm and not waste time on the other one. To do this, we look at the growth rate of the algorithm as the number of items it operates on grows towards infinity. For example, if we only have to run the algorithm once on a small number of items, efficiency really doesn't matter. But what happens if we have to run that algorithm many times on millions of items? The efficiency of the algorithm then becomes very important, especially in game development, as we need all of our algorithms to run in real time. We need to carefully consider efficiency as we implement our code. Inefficient algorithms could kill your frame rate. We use BigO notation to analyze the growth rate of an algorithm. BigO notation represents the worst case analysis of the algorithm based on its growth rate as the number of items grows towards infinity. We sometimes call this the order of the algorithm. To find the worst case growth rate, we safely ignore constants and lower orders of n. For example, 3n has a worst case growth rate of n. So we ignore the constant and simply say that 3n is BigO of n, or 3n is order n. Consider 15n squared plus 5. In this case, since 5 grows more slowly than n squared, we ignore the 5, leaving us with 15n squared. Since 15n squared has a worst case growth rate of n squared, we ignore the 15 and say that the function is BigO n squared. Finally, let us consider n to the sixth plus 3n squared. In this case, since n squared has a slower growth rate than n to the sixth dominates this function, so we can safely ignore the n squared term entirely, leaving us with 2 times n to the sixth. Since 2n to the sixth has a worst case growth rate of n to the sixth, we consider this function BigO n to the sixth. While the examples we explore in this lesson are focused on efficiency and time, the same analysis can be used to evaluate the memory consumed by two algorithms. We will look at such an analysis in a later lesson. So now that we can compute the BigO of an algorithm, how does this help us compare algorithms? If we are evaluating the efficiency of two different algorithms, instead of implementing them both, which might take a tremendous amount of time, we can examine their BigO and then decide based on our intended use. Here we have two algorithms we must compare. One runs in 1000n time and the other runs in n squared time. How do we know which is better? We focus on their growth rate by determining the BigO of each. 1000n is BigO of n, while n squared is BigO of n squared. Since order n, or BigO of n, is less than order n squared, we conclude that the algorithm that runs in 1000n time is a better choice if we will have more than 1000 items. However, if we will have less than 1000 items, it actually turns out that order n squared is the better choice. Generally, we only really care about these questions of efficiency when n grows very large, though, so it would rarely make sense to implement the n squared algorithm. There are other ways to compare algorithms too. As we just learned, BigO represents an upper bound. Big omega represents a lower bound, indicating that an algorithm's growth rate is always larger than the big omega function. Big theta represents both the upper and lower bound if they are the same efficiency. Finally, little o represents an upper bound that is strictly less than. Usually we are only concerned with the big O growth rate, as this represents the worst case scenario. But if two algorithms have the same big O, we may use these other bounds to determine which is better for our given application. For example, if one algorithm is big O of n and the other is little o of n, the one that is little o of n is the better choice if everything else is equal. Let's take a look at a few examples. As we just saw, big O represents the upper bound of the growth rate. So 2n squared is big O of n squared. 2000n squared is also big O of n squared. 16n squared minus 4n is also big O of n squared. 15n cubed plus 37n squared minus 4n plus 92,674 is big O of n cubed. Big omega is the lower bound of the growth rate, so n cubed is big omega n squared. However, this is an example of a loose bound. We can make a tighter estimate, but it is still true that the growth rate for n cubed is greater than that of n squared. 6n cubed plus n squared is big omega of n squared. Big theta represents the upper and lower bound. 2n squared is big theta n squared since the growth rates are identical. Finally, little o represents a strictly less than upper bound. So n squared minus n is little o n squared since its growth rate will never match that of n squared. Here are some common growth rates that we usually use to compare algorithms in order from smallest growth rate to largest growth rate. On the right, you can see a graph with some of these functions and their associated growth rates. Looking at the linear growth rate, where f of n equals n, this is usually considered an acceptable growth rate for many algorithms. Linear growth means that the work the algorithm does is directly proportional to the number of items. If you needed to add n items to a list, it would take n operations to do so. In this way, linear growth is assumed to be a reasonable cost for many actions. However, looking at this graph, we see that log n has a slower growth rate than n, indicating that logarithmic algorithms have better performance. Hidden behind the logarithmic growth is constant growth. This indicates that no matter how many items are in our collection, the action requires the exact same amount of time. Constant time growth is the ultimate performance goal, but is often very hard to attain. Unfortunately, we also can quickly see why quadratic, exponential, and exponential base n are such horrible growth rates. They grow substantially faster than linear, and therefore will be very expensive. Naive approaches to collision detection and sorting may take quadratic time. When there are millions of objects, this becomes unacceptable. Our final step in attempting to estimate the complexity of an algorithm is to understand where we get the constants and exponents to use in our function in the first place. Since computing technology is constantly increasing in speed and memory, there is no point in analyzing an algorithm based on the actual time it takes to run. Instead, we base it on the number of operations. So basic statements like addition, subtraction, assignment, and other computations are considered to be one operation and therefore take one time unit. Using this as the basis for our calculations, we then use addition and multiplication to determine the number of time units other blocks will take. If we have consecutive statements, we add their runtimes together. For an if, else, or switch case statement, select the longest branch and use its runtime. For loops, sum the number of statements inside the loop and multiply by the number of iterations of the loop, and then add any loop control statements. For nested loops, compute the inner loop and then multiply its time by the number of iterations of the outer loop. In this initial example, we have an if-else statement. The if test itself is a single operation, and then there is one operation if the expression is true, and one operation if the expression is false. So we add the time for the longest branch, which is 1, to the time to compute the branch itself for a total of 2 operations. Since this does not change regardless of the size of n, this method is a constant time or order 1 operation. Here we have a simple loop. Creating the partial sum variable is one operation. Initializing the for loop is one operation. A test and an increment are performed each iteration of the loop, and then within the loop, we have 2 multiplications, an addition, and an assignment for a total of 4 operations for each iteration. Since I goes from 1 to n, there are n total iterations. We take the 2, add the 4, multiply by n, and then add 1 for the initialization to get 6n plus 1 actions to complete the loop. We then return the value of partial sum for a cost of 1 more operation. So 1 operation before the loop, 6n plus 1 operations to run the loop, and then 1 operation after the loop. The total cost of this algorithm is 6n plus 3. We ignore the constants and find that this algorithm is big O of n, or a linear algorithm. Finally, we have a more complex example with a nested loop. First, we examine the outer loop. We find that there is 1 operation for the initialization, 2 for each iteration, and n iterations. At the end of this outer loop, there is 1 more operation, the right line. So the total time for the outer loop is 3n plus 1. The inner loop is essentially the same. 1 for the initialization, 2 for each iteration, 2 write statements, and n iterations for a time of 4n plus 1. We then take the time for the inner loop and multiply it by the number of iterations for the outer loop. Multiplying this all out, we get 4n squared plus 4n plus 1. Realizing that the growth rate of 1 is less than that of n squared, and that the growth rate of 4n is less than that of 4n squared, we replace these with the higher growth rates, sum them all together, and end up with 9n squared, which is big O of n squared.